There was a time, let's say 20 to maybe 30 billion years ago, when the universe as we know it today did not exist. In fact, at that time, time itself did not exist in the same way that we experience it. There was nothing. But try and imagine nothing, it's nearly impossible. The first thing that might come to your mind is darkness. But even darkness is something, it's darkness. Okay, maybe empty space. Empty space is something. Because it's empty doesn't mean it's nothing. Our minds are wired to understand and experience the world through objects that exist in space and time. But what if we rewind time to a point where the universe, as we know it today, did not exist? What was there before? The concept of nothingness is shrouded in paradox. It's an absence that can only be defined in the presence of something. Even in the vast emptiness of space, there is always something present, making it hard to imagine a state of pure nothingness. When scientists discuss nothingness, there is often disagreement about what it really means. The definition of nothingness varies depending on the context and language used. However, scientists have tried to explore this concept and have come up with different theories and equations to understand how the universe came into being from nothingness. Keep watching to find out more. One of the earliest Western philosophers to consider nothing was Parmenides, who argued that nothing cannot exist. He believed that to speak of a thing, it must exist, and since we can speak of things in the past, they must still exist in some sense now. From this, he concluded that there is no such thing as change and that nothing can come into being, pass out of being, or not be. While Parmenides' reasoning on nothing was largely agreed by other philosophers such as Socrates and Plato, Aristotle differed in his conception of nothing. He believed that while these opinions may follow logically in a dialectical discussion, it would be next to madness to believe them when considering the facts. Fast forward to modern times, and Albert Einstein's concept of spacetime has led many scientists, including himself, to adopt a similar position to Parmenides. Einstein believed that the distinction between past, present, and future is only a stubbornly persistent illusion, and that time is relative. Different physicists see different things as nothing, from nothing as a classical vacuum, to the idea of nothing as undifferentiated potential. Even if you could remove all the particles in a box, and shield it against all electric and magnetic fields, your box would still contain gravity, because gravity can never be shielded or cancelled out. Gravity doesn't go away, and it's always attractive, so you can't do anything to block it. According to Newton's physics, it's because gravity is a force, but in general relativity space and time are gravity. Okay, let's imagine we could remove gravity, and every other thing from the system, you'd be left with a true vacuum. Even at its lowest energy level, there are fluctuations in the quantum vacuum of the universe. There are quantum particles popping into and out of existence throughout the universe. There's nothing, then pop, something. And then the particles collide and you're left with nothing again. And so, even if you could remove everything from the universe, you'd still be left with these quantum fluctuations embedded in space-time. You see why it's difficult to just conclude that nothing exists. It's probably better to think of nothing as the absence of even space and time, rather than space and time without anything in them. The laws of quantum mechanics are confusing, predicting that particles are also waves and that cats are simultaneously alive and dead. However, one of the most confusing of all quantum principles is called the Heisenberg uncertainty principle, which is commonly explained as saying that you cannot simultaneously perfectly measure the location and movement of a subatomic particle. While that is a good representation of the principle, it also says that you cannot measure the energy of anything perfectly, and that the shorter the time you measure, the worse your measurement is. Taken to the extreme, if you try to make a measurement in near-zero time, your measurement will be infinitely imprecise. This means that there is always a minimum level of uncertainty in the universe, even in empty space. But what does this mean for the question of whether or not nothing exists? It means that even if we were to completely remove all matter, energy, and other physical properties from a particular region of space, there would still be some level of uncertainty present. This uncertainty arises from the quantum fluctuations that occur in empty space, as particles and antiparticles spontaneously pop into and out of existence. In the beginning, there was a bang. This is what almost all scientists believe to be the beginning of the universe. That it all began from a state of extraordinary compression and phenomenally high temperature in which forces such as gravity and electromagnetism were unified in a single, all-encompassing force. A singularity. But for most of the century, scientists puzzled over this. Why, if its original state was chaotic, is the universe of galaxies as uniform as it appears? Why is the universe precariously perched between expanding infinitely and collapsing back on itself, between being conducive to life and being totally inhospitable to it? The recent, surprising progress toward answers to these questions has been made possible by the increase in physicists' understanding of the connection between the biggest and smallest things in the universe. Through the work of astrophysicists and particle physicists, it is becoming possible to meld together the realm of stars and galaxies, and the world of subatomic particles and waves. Many features of today's universe make sense if space underwent an extraordinary expansion very early in its history. According to inflation theory, the universe expanded dramatically a tiny fraction of a second after the Big Bang, driven by fantastic quantities of energy contained in space itself. After this period of inflation, the universe continued to expand and cool, but at a far slower pace. The universe went through several epochs or eras, each characterized by different physical conditions and dominant forces. The first epoch is called the Planck era, which lasted from 0 to 10 to minus 43 seconds after the Big Bang. During this epoch, the universe was incredibly hot and dense, and the four fundamental forces, electromagnetism, gravity, strong nuclear force, and weak nuclear force, were unified. Next, the universe entered the Grand Unified Epoch, which lasted from 10 to minus 43 seconds to 10 to minus 36 seconds after the Big Bang. During this epoch, the strong nuclear force separated from the other three fundamental forces, leading to the formation of quarks and other subatomic particles. Following the Grand Unified Epoch, the universe entered the electroweak epoch, which lasted from 10 to minus 36 seconds to 10 to minus 12 seconds after the Big Bang. During this epoch, the strong nuclear force was separate from the other two fundamental forces, electromagnetism and weak nuclear force. The universe was filled with a plasma of subatomic particles and radiation. After the electroweak epoch, the universe entered the particle era, which lasted from 10 to minus 12 seconds to about 380,000 years after the Big Bang. During this epoch, the universe was dominated by radiation and subatomic particles, and the first atoms began to form. Finally, the universe entered the era of structure, which lasted from about 380,000 years to several hundred million years after the Big Bang. During this epoch, the universe continued to expand and cool, and gravity began to pull matter together to form the first galaxies and stars. But what if it were possible to reconcile the notions of an eternal universe with the Big Bang? Is it possible for us to have our cosmological cake and eat it too? Eventually, as the universe becomes more disordered, structures will decay, stars will die, and even black holes will evaporate. The increasing entropy of the universe will ultimately lead to the heat death of the universe. At this point, there won't be much left apart from cold, dark space and the occasional photon traveling forever into the void. Physicist Roger Penrose suggests that the universe has an infinite cyclic history, with each cycle beginning with a Big Bang and ending with a Big Crunch. In this theory, the universe is viewed as a conformal geometry, meaning that the geometry of space-time is preserved even when it is scaled by a factor. This allows for the universe to exist in an eternal state of self-replication, with each cycle identical to the one before it. This model is what we refer to as conformal cyclic cosmology. That our universe is one of an infinite lineage of universes, and will ultimately become the progenitor to the next in the chain. The Big Bang is both the start of our universe and the death of an older universe that came before. In other words, the conformal cyclic cosmology suggests that the Big Bang is not the beginning of the universe, but rather a transition point from one cycle to the next. Since the universe is viewed as existing in an infinite and eternal state of self-replication, the concept of nothingness is not necessary for the universe to exist. Instead, the universe can be seen as a self-contained entity that perpetually cycles through states of expansion and contraction. One of the most profound testable predictions of this model is that we should be able to see the remnants of dying black holes from the previous universe. The radiation left over from the evaporation of supermassive black holes might travel across the boundary from the end of one universe into the next. It's just a case of spotting temperature fluctuations when we observe the radiation in the sky. The twin pillars of modern physics are Einstein's general relativity and quantum theory. The Wheeler-DeWitt equation is an attempt to combine these two theories. Quantum mechanics deals with the behavior of matter and energy at the smallest scales, while general relativity describes the behavior of gravity at the largest scales. The problem is that these two theories seem to be incompatible with each other. For example, general relativity predicts the existence of black holes, which are regions of space where the gravitational field is so strong that not even light can escape. However, quantum mechanics predicts that information cannot be destroyed, which creates a paradox because the information that falls into a black hole seems to be lost forever. The Wheeler-DeWitt equation attempts to solve this problem by describing the universe as a wave function. The wave function describes the probability of finding the universe in a particular state at a particular time. The equation removes time from the equation, treating the universe as a timeless entity. Despite its importance, the Wheeler-DeWitt equation is not a complete theory of everything. It only describes the universe as a static entity and cannot explain how the universe evolves over time. Moreover, it is not clear how to interpret the wave function of the universe or how to test it experimentally. The uncertainty principle, which is a fundamental principle of quantum mechanics, also plays a role in the Wheeler-DeWitt equation, which we have talked about before. However, it states that it is impossible to know both the position and momentum of a particle with absolute precision. This means that there is always a degree of uncertainty in our measurements. The Wheeler-DeWitt equation incorporates this uncertainty into its description of the universe, which helps to account for the unpredictable behavior of matter and energy at the smallest scales. Another candidate is string theory, which views the basic building blocks of reality as tiny strings of mass energy vibrating in 10-dimensional spacetime. If we are able to obtain a theory of everything, will we be able to answer the ultimate questions? What is space? What is time? What is the universe? Where did it come from? And how it began from nothing? Maybe space is like a phoenix in an eternal cycle of life and death. Maybe time repeats itself in an infinite recurrence of the universe after universe. Or perhaps this is the only universe after all, with a small, hot beginning and a cold, dark finale. Until the day comes when we discover how to extract more information from the universe than presently seems possible, we have no choice but to face our ignorance. The Big Bang still happened a very long time ago, but it wasn't the beginning we once supposed it to be. Some even go as far to say that the universe is not real, that everything we see, touch, or experience is just a story being created by our brain. I've already made a video on that. Click the video on your screen to find out more. Thanks for watching, and subscribe for more video.